Can you hear me okay? If anyone would like a hearing assist device, we have a number of them, and if you would want one, just raise your hand now and Chris or someone will bring you one. Okay. Well, it's great to see all of you, and welcome to the second annual Imagine Lecture established in honor of David B. Winter. I'm Dr. Terry Borman, and I'm a member of the planning committee for this event. The intent of the lecture series is to remember Dr. Winter and to stimulate all of us to imagine as David did in his life. At the bottom of Dave's emails was the word imagine. This highlighted his commitment to lifelong learning and a passion for those who pursued the limits of human performance. Dr. Dave Winter is remembered as a son, a brother, a husband, a father, a radiologist, a colleague, and a friend. In his work and personal life, he continually pursued learning and exploration of new ideas. He did his work exceptionally, but not only that, he went beyond what was expected of him, making work better and easier for all of his colleagues. Last year, the first Imagine lecture was presented by David's father, Dr. Robert Winter. His inspirational talk on lifelong learning as a world-renowned spine surgeon was a wonderful start to this event. Today, we have an opportunity to truly imagine. Dr. Ed Stone, a friend of the Winter family, joins us. He is a truly remarkable man and has been deeply involved with exploring our solar system and the depths of space. His career has included time at the Jet Propulsion Laboratory, and he is now a professor at the California Institute of Technology. For the past 35 years, as the project scientist, he has been intimately involved with the mission of the Voyager spacecraft. Please welcome Dr. Ed Stone to present today's Imagine lecture, Voyager, a Lifetime Odyssey of Discovery.
Thank you very much. It's really a great privilege to be here to celebrate this evening. I didn't know David Winter, but in fact, I really feel a bond because, in fact, you're going to hear a lot about digital imaging this evening. You're going to hear a lot about learning new things and imagining things. So I think, in that sense, it's really I'm very pleased to be here. So, a lifetime odyssey of discovery. And it really, actually, the mission itself began a little bit before that, 1965, when a graduate student, I was at Caltech, I had arrived at Caltech in 1964 to set up a space physics group, and I was not aware that this was going on at JPL at the time, but a graduate student was working at JPL in the summer of 1965, looking for ways to take advantage of when you fly by a planet, using the planet as a slingshot to speed the spacecraft on its way. And what he found was that if you launched a spacecraft in 1977, plus or minus 1 year, a spacecraft could fly by all 4 giant outer planets, Jupiter, Saturn, Uranus, and Neptune. This is an alignment of planets that happens every 176 years. So this was a rare opportunity. So the Jet Propulsion Laboratory began to plan for a mission that would, in fact, be able to take such a journey, one which would take 12 years at a minimum to go from Earth out to Neptune. That was considered much too ambitious for the time and much too expensive, and what was decided instead was to do it step by step. Start launching in 1977, but launch just a mission to Saturn. So the original idea was to launch 2 spacecraft, and we launched 2 because we weren't sure that both would survive for that long. Remember, when Voyager was launched, the space age itself was only 20 years old. So we launched 2 spacecraft, flying by Jupiter, getting a slingshot on its way out to Saturn, and at Saturn it flew by Saturn at such a way that it ended up being propelled up out of the plane of the planets as shown in this diagram. Following along behind was Voyager 2, which, because Voyager 1 was successful at Saturn, we could leave it at the plane of the planets, swing by Saturn, and get us push on to Uranus, and finally on to Neptune. That would complete the 12-year planetary phase of the mission. But it was being done step by step, and the original mission success was just a 4-year mission to Saturn. That was the original mission success for Voyager. Here's the spacecraft. This was the first fully automated spacecraft. It flies itself. It had to do that because these planets are so far away that you cannot command them in real time, because it takes hours for light to get back from the outermost planets. So the main thing you see on the spacecraft is the 12-foot radio antenna, which faces Earth 24 hours a day and sends a steady stream of data back to Earth. One thing that keeps the spacecraft powered, the thing which keeps it powered with electrical power, are these units here, which are called radioisotope thermoelectric generators. The natural radioactive decay of plutonium-238 creates a very hot source. You bolt thermocouples to the source, and that generates electricity. A very simple, robust power supply. The radioactive half-life of plutonium-238 is 88 years. So in 88 years, the power is half as much as it was when the beginning. That's one reason why the spacecraft can still operate today, because of those very robust power supplies. The science instruments, scan platform, which pointed all the cameras. These were the first some of the first digital imaging cameras. The first one was actually flew by Mars in 1964 and returned digital images of Mars. And Voyager produced the first digital images from the outer solar system. So the things you'll be seeing tonight are all digital images that were, at their time, of course, quite remarkable. Today, we all have them on our laptop computers in our living room. Digital imaging is everywhere. And of course, hospitals in particular, digital imaging has been a revolution. But Voyager basically had these two digital imaging cameras on board, along with some other instruments. And the other instruments looking at the particles coming from the sun that I'll talk about later. This long boom, which is 43 feet long, has the instruments on it to measure the magnetic field, which is very weak out there, and I'll talk about the magnetic field as well when I get to the interstellar phase of this mission. Well, here's the interest in those giant outer planets. Launched in 1977, we celebrated our 35th anniversary just last week. For the launch of Voyager 1. Jupiter, these are now images to scale. So you can see that here's the Earth. Jupiter is, and all of these planets are giants compared to the Earth. The Earth, the inner planets like the Earth are rocks. Mercury, Venus, Mars, and Earth are rocky objects. These are giant spheres of fluid, gas and fluid. No solid surfaces on them at all. And very different than the planet that we live on and the planets that had been visited before that. The distance out from the Earth to the Sun is 1 astronomical unit, 93 million miles. So part of the challenge a mission like this has is that Jupiter is 5 times as far from the Sun as the Earth. That means the sunlight is 1/25th what it is here. The energy that's available is 1/25th. On to Saturn, 10 times as far from the Sun as the Earth, and therefore the sunlight is 1/100th, and the signals coming back to Earth are 1/100th as strong as if they were coming to Earth from the Sun. And on to Uranus, now 19 astronomical units. And finally, Neptune, the furthest, 30 astronomical units from the Sun. The sunlight out there is 1/900th of what it is here. That's the reason solar panels were not an option for flying a mission deep, deep into space. And of course, the communication time scales. It's 8 minutes for the Sun at Earth, and by the time you're at Neptune, it's 240 minutes light time back to the Earth. So you can see the reason the spacecraft had to be automated spacecraft. So we flew by Jupiter, a lot of discoveries. We knew about the Great Red Spot. It had been seen on Jupiter's atmosphere for 400 years. What we discovered is a huge hurricane-like storm system. Remember, the Earth's about the size of that storm system. What we discovered was not only was this a huge storm system, but every one of these other things that you see, all these white spots, are huge storm systems riddling the atmosphere of Jupiter. Here's a whole stream of them. Here's another stream of them. And the reason the Great Red Spot persists so long is because these smaller storms come around and interact with it and basically can spin it up and keep it in its hurricane-like strength. The two moons, Io and Europa, are really some of major discoveries that Voyager made. Before Voyager, the only active volcanoes in the solar system that were known in the solar system were here on Earth. No other planet had active volcanoes. And yet, when we flew by Jupiter and flew by its moon Io, we saw this. And it's a surface which had no impact craters on it. We know things have been hitting Io, but you could not see any impact craters. Instead, we saw these black spots. It turns out they're lava lakes. This moon has 10 times the volcanic activity of Earth. In fact, we saw 8 volcanoes erupting, some of them hundreds of miles high. So our terracentric view that the Earth was so unique in the sense it had active volcanoes suddenly had to be greatly expanded. And then there was Europa, the same size moon as Io, looks totally different. It's covered with water ice. And what we discovered is these features you see are just small cracks in the surface. There are no mountains, there are no valleys. This is the smoothest surface in the solar system, suggesting that in fact this is ice on an ocean beneath the surface. Again, before Voyager, only Earth had a liquid water ocean. And now it appeared that Europa might also have one. On to Saturn. This is an image taken by Voyager 1 as it left and was heading up out of the plane of the planets. So we're looking down on Saturn. The first time we could had a camera out beyond Saturn to look back. You can see the shadow being cast on Saturn's rings. You can see the incredible detailing in the rings of Saturn, which we discovered were caused by the wakes of moons, both inside the rings and moons which are orbiting outside, but interacting with the rings to create the waves which you see there. There were 2 moons of Saturn, which also were important for us. This is Enceladus, which is a small icy moon. It's about 300 miles across. This is what we expected we would see, a heavily cratered, ancient icy surface. We did not expect to see evidence for faults, as though look at these cracks. They look just like earthquake faults on this tiny little world. We did not know at the time why. We knew this is the whitest object in the solar system, so white that it reflects almost all of the sunlight, and therefore it's quite cold. And it's white because it turns out the Cassini mission, which is now orbiting Saturn, discovered geysers of water erupting from the south polar cracks on this moon, Enceladus. So there's a liquid water reservoir of some sort in this tiny moon, heated by some mechanism, perhaps tidal effects, which in fact then drive the geysers and coat the moon with its snowy brightness. And then there's the moon Triton. Triton looks fuzzy because it, unlike the Earth before Voyager, only the Earth had a nitrogen atmosphere. Triton now has one. In fact, it's 60% more higher pressure than here on Earth. So again, our view of the Earth and its comparison to the solar system began to change even more. So this moon has a really deep atmosphere, and you cannot see the surface in the visible light because what causes the smog here on Earth, the action of sunlight on our atmosphere, turning things into various kinds of oxides. On Triton, there is no oxygen in the atmosphere. There's methane, there's natural gas. And so the action of sunlight is to make organic compounds, some of which polymerize and create a haze layer that cannot be seen through. Fortunately, the Cassini mission has returned to Triton because we said there should be a water cycle on Triton, but the water cycle won't be water, it will be methane. That is, there'll be lakes of liquid methane, liquid natural gas, evaporating, creating clouds of methane, which then rain back down on the surface. When the Cassini spacecraft returned some years later in the year 2004, went into orbit, it carried a probe built by the European Space Agency, which plummeted down into this atmosphere and took this image on its way down. And it certainly looks like dry riverbeds formed by evidently the rain of such materials as liquid natural gas. And it looks like these perhaps were dry lakes. Well, it turns out the Cassini spacecraft has on it a radar system that can peer through the haze layer. And when it did that, it found the lakes of liquid methane and other ethane and other hydrocarbons. Some of these are as large as the Great Lakes. These are not tiny little ponds. These are large lakes, mainly in the polar region where it's cold enough that they can remain in a liquid state. The temperature there, by the way, is only about, it's 94 degrees above absolute zero, which is minus 183 degrees Celsius, something like that. Very cold. And the chemistry which is going on there today may resemble the chemistry that occurred in the Earth's atmosphere before life evolved and gave us the oxygen we breathe. On to Uranus, which is now almost 20 times as far from the sun as the Earth. Much less energy, about 1/400th of the energy to drive the weather systems, and indeed, it's a rather bland atmosphere. You see, if you look carefully, you can see a few white clouds. By the way, the pole of rotation is right here. Uranus is tipped on its side, evidently tipped over as it was being formed by the impact of large objects, and there was one large enough, perhaps as large as Mars, which then tipped Uranus over, and with its pole now, at this time, facing the sun. Now, before Voyager, all the known magnetic fields that were like Earth's, that is, the north magnetic pole or a magnetic pole is up near the rotation axis of the Earth. That makes it very convenient as a compass, because magnetic north is very close to geographic north. That's also true in Saturn. It was true on Jupiter. It was true on Mercury. Venus doesn't have a magnetic field. But guess what? The magnetic pole of Uranus was nearer the equator than the pole. And that was kind of a contradiction, because we knew that the rotation of the planet is what generated the magnetic field, and therefore the field should have the symmetry of the planet, should have the same kind of pattern as the planet. It does not. In fact, it means that, in fact, the flow inside of Uranus is not a huge system rotating with the planet, but much smaller sort of cyclone effects which generate this offset and tilted dipole. Turns out Neptune is the same way. And another surprise at Uranus was the small moon Miranda, again about 300 miles across. Tiny little world, frozen water ice mainly and some rock. This is what we expected to see, a bright icy surface with lots of impacts caused by the rain of meteorites over billions of years. But look at this. Each of these streaks you see is a fault system, a series of steps in a raised plateau, another series of faults creating this little check mark on the side of Miranda. And if we look down there, you'll see a cliff miles high on a moon which is only 300 miles across. This is the most complex body in terms of its surface that we've seen, and again suggests this world had, at least for a period of time, a very active geologic life. There is no evidence that that's true today, but in fact it's now a frozen relic from an earlier episode of activity. On to Neptune. Now, 30 times as far from the sun, 1/900th of the sunlight, 1/900th of the energy to drive the winds. And guess what? The fastest winds in the solar system are in Neptune's atmosphere. The fastest winds when you have the least energy. This great dark spot does not have the same longevity as the great red spot. It's now gone, so it was a temporary feature. But there aren't lots of other spots to feed it, so perhaps it's just the fact it was all by itself and was not stable for a long period of time. And the very last body we measured as we left the planets behind was the moon Triton, which is captured around Neptune. It was originally in orbit around the sun, very much a twin of Pluto, we believe. But it was captured by Neptune. We know it was captured because it's going around Neptune backwards. On the Earth, the moon and the Earth rotate in the same direction. That's true of all the moons that I've showed you. All the regular moons all orbit around the same direction as the planet rotates because they formed out of the same rotating cloud. When a moon is rotating the opposite direction, it was captured. So this moon was captured. It was a separate world that was captured. It had a very violent activity to essentially dissipate the energy of that capture, and that left us with this surface features you see here, which are with faults and so on. So there was a period of a lot of geologic activity as this moon was being captured by Neptune. We had never seen anything like this before, and this is the only body that we've seen that has this, what we call Cantaloupe Terrain. Now, this is the coldest body we've seen. It's the furthest from the sun that we visited. It's the coldest. It's only 40 degrees above absolutely zero, minus 233 degrees Celsius. So cold that what you're looking at in the polar cap is not frozen water ice. That's what most of all this is. This is frozen nitrogen. So the nitrogen in the atmosphere is frozen into a nitrogen ice pack. But once again, if you notice these dark streaks, it turns out there are geysers erupting out of that icy polar cap at 40 degrees above absolute zero. So even in the absence of any sensible amount of energy, nature has contrived a way to have geologic activity. So it just time after time, Voyager discovered things that just completely changed our view of the solar system and gave us I think, a new understanding, not only of these bodies we'd seen, but in fact, we have to look again at our understanding of Earth, because we recognize that Earth is not nearly as unique in having certain properties as we thought. This was the planetary part of the mission. It was a 12-year phase. We went step by step. We did 4 years to Saturn. Mission success allowed us then to start what we call the Voyager Uranus interstellar mission, because Voyager 1 was on its way to interstellar space. After the Uranus encounter was successful, then we got an extension for another 3 or 4 years to have the Voyager Neptune interstellar mission. And then in 1990, we formally started what was then called the Voyager Interstellar Mission. And that's the mission we've been on now for 22 years, a mission to leave the planets, to leave the solar system, to leave the sun's bubble around the planets, I should say. What is that bubble? What is the sun doing? Well, in this sketch, this is a cartoon. Here are the planets, here are the orbits of the planets, roughly to scale. And the sun has a wind blowing radially outward from it. It's a solar atmosphere expanding at 1,000,000 miles per hour, creating a huge bubble of plasma, or of ionized gas around it, a plasma. That bubble extends well beyond all the planets. In fact, I was showing you how close we think we are to leaving the bubble. So there is a surface to this bubble. Inside that surface, called the Heliopause, the material has come from our sun. Outside, the material has come from other stars. And so there is a clear demarcation between inside and outside. This is interstellar space. This is the sun's heliosphere. We knew that object was out there, had been predicted in 1961. We just didn't know how big it was, because its size is determined by a balance in the outward pressure from the sun balancing the inward pressure from the interstellar wind. And although we were measuring what was inside, and we knew what the pressure was inside, we had no direct measurements of what's outside. And so we didn't know exactly how big the bubble might be. And therefore, we didn't know whether the Voyager spacecraft would actually eventually enter interstellar space. So it all begins with the sun. This is a movie. This is actual data now. This is not a cartoon. And if I get my arrow up here, here we go. This is taken by the SOLHO spacecraft, which is out in front of the Earth looking at the sun 24 hours a day. And you can see the sun rotates. It has a 26-day period of rotation, which appears to be about 27 days because the Earth moves a bit while it's rotating. And you can see the series of sunspots developing. These are the spots which come and go with an 11-year cycle. We're now approaching a period of maximum solar activity where the maximum number of sunspots are there. And the sunspots, when they erupt, are part of the sun's magnetic field changing polarity. Every 11 years, what was up in the north of the sun in the magnetic field, it turns to the south. So every 11 years, the magnetic field of the sun reverses polarity. And it happens on the Earth roughly every 1,000,000 years. It happens on the sun every 11 years, plus or minus. And it's that magnetic field which is in fact the source of the energy which drives the supersonic wind. If we go a little bit higher above the photosphere, now looking in the wavelengths which correspond to plasma with temperatures of 1,000,000 degrees or so, we see a different view of the sun. We see those magnetic fields. You can see the loops of the magnetic fields varying, fluctuating, changing, and whenever you see these magnetic fields changing in a great way, the energy they dissipate fuels and heats the corona of the sun to 1,000,000 degrees, and that causes it to expand supersonically away. And that is what you can see in this coronagraph from SOHO. So this is an image where there is a disk in front of the sun. So the sun is the size of this white circle. The disk blocks the sun so it doesn't blind the camera, and that allows one to see the corona. Of course, if you see a total solar eclipse, you can actually see this by eye. It's always there. And what you can see in this image, this movie, again from SOHO, of the light reflected back off of the corona, expanding away from the sun, is the outward flow of the gas. But you can see here's a comet, and you can see its tail being blown backwards by the solar wind. You can see eruptions. When the sun has a lot of activity, there'll be large eruptions from the sun. There'll be one coming up in a moment. They're like that. When those blast waves move out into space and hit the Earth, they cause the aurora to move down to much farther south. They can interrupt power grids here on Earth, damage spacecraft in orbit around the Earth. So this is part of space weather. So you can see what this image shows you, though, is this wind is blowing radially outward, straight out, radially, in all directions, supersonically, 1,000,000 miles per hour, and it just keeps going further and further out, getting thinner and thinner, but not slowing down. It doesn't slow down until it finally gets close to the boundary, and then it slows down in a shock. Just like a supersonic aircraft, there is a shock. And that shock forms as the supersonic wind approaches contact out here. It has to start to turn to go down the tail. It can't keep going radially. And it can't turn until it becomes subsonic. And that's what happens in front of a jet aircraft. The wind becomes subsonic. It's a shock and turns and flows down the tail. So that's the first key signature of how large the heliosphere was how far it was out to the end of the supersonic solar wind and the beginning of the subsonic flow turning to go down the tail. Now this is just a cartoon, obviously, of just taking you out quickly past the planets, heading out, sort of schematically trying to show you a picture of what I just told you. You can see the solar wind represented by these lines streaming out. Here's that boundary, that shock, where the solar wind suddenly slows, and you can see it turns and flows tailward down the tail. The tail is where all the wind has to end up going. And you see the interstellar wind comes and is deflected around this, the heliosphere, which acts like a big blunt object to the interstellar flow. This next short cartoon is just to help you understand the scale of the heliosphere on a galactic scale. This is a spiral galaxy, not sort of similar to our Milky Way galaxy. This is one of the arms of the galaxy. We're going to zoom into it and zoom further in and in and in, and suddenly, finally, you see the little heliosphere. So on a galactic scale, this is a very tiny object. Every star can have one of these spheres around it, which is drawn into this comet-like shape if there's an interstellar wind blowing in a particular direction. So they act like an interstellar wind shock, pointing the direction away from the interstellar wind. What's around our local sun? What's actually, do we think, is outside pushing? Well, this is again a cartoon, but it's actually based on data, which is what astronomers can do is observe stars. So you're sitting here at Earth, you observe a star coming, starlight coming like this, you observe starlight coming in this direction from another star. You look at as many stars as you can from all the directions, and you can detect whether there's material in the way because it absorbs some of the starlight. And when you put all that data together, it's sort of like tomography, computer tomography, X-ray tomography, except it's done with UV light. You can reconstruct what you think the clouds might look like. And the current model is that there's a cloud which was the result of the explosion of many massive stars 5, 10, and 15 million years ago nearby the sun. And as those stars blew up, they ejected most of their mass into big shells of material, which then merged into giant bubbles. So this is our heliosphere is a big bubble from our standpoint, but it's small compared to this big bubble, which was created by a bunch of stars blowing up. And we're in the edge of one of these bubbles. We have been for about 100,000 years. One of these clouds from which were these ejected by all these stars blowing up. And we know that it's the combination of the direction of the exploding material, which is in this direction, and the motion of the sun in this direction, which in fact combines to give us the wind, which we sense when we look out into interstellar space. So they really do exist, these things. This is a real image now. This is from the Hubble Space Telescope. This is an Orion Nebula where there's a lot of star formation going on. A lot of big stars form and blow up. And you can see here is a star. There must be an invisible astrosphere because you see the big shock in front of it from the interstellar wind, which is coming from this direction. If you look up here, you'll see another little astrosphere. We're inside of one of these things on our way out. That's the mission we're on. Now, I can't show you a digital picture of our heliosphere, but I can show you a digital photograph of our sink. Yes. Every sink, you'll see an analog of the heliosphere. You may have noticed this. That is when you turn the water on, you leave the drain of the sink open so the water drains, and when you do, you notice that where the water hits the bottom of the sink, it rolls radially outward in all directions. And it's flowing very fast, and it's very thin. And it just keeps expanding, but it's getting thinner and thinner, but doesn't slow down. Notice it is not slowing down. It's moving faster than the waves in the water, on the surface of the water. Therefore, in that sense, it's moving faster than the speed of sound. It's the speed of actually the waves on the surface. But eventually, it has to slow down because it's getting thin, and it slows down in an abrupt shock, just as the solar wind does. And then it slows, forms a thick ring, because that water has to go somewhere, so it piles up, forms a thick ring, and then it turns and goes down the drain. So every time you look in your kitchen sink, think this way. Okay? There's the solar wind. Here's the heliosheath, where the wind is turning to flow down the tail of the heliosphere, and on the outer edge is the heliopause, the boundary between what came from the sun and what is coming from outside. So that's what we're exploring. And right now, the two Voyagers are in that thick ring of solar wind where it's slowed down, and I'll tell you what we have learned so far about it. So here is a mathematical model, not a cartoon, a real mathematical model, which shows the feature I've just described. That is, here's the sun. You notice the ions, the wind is radially outward, perfectly radially outward until this jump. What's the color is temperature. So this is a cooler wind, only 10,000 degrees, and then it jumps at the shock to a 1,000,000 degree wind, where then you notice then it starts turning. Wherever these lines from the wind cross the shock, they start turning. That's exactly what we think is happening in the solar wind. And here's the interstellar wind, which is deflected around the outside, as shown by these flow lines. So one of the first steps was to look at this shock. This shock where the wind abruptly slows down. It turns out what happens is because on upstream of the shock, the wind is going 400 kilometers per second, and after the shock, it's only moving 100 kilometers per second. If you like, particles can bounce back and forth across the shock, and some small fraction of them can gain a few percent the speed of light, which is really fast. And those are called energetic ions. And our first indication of the shock will be when we see the source of these ions at peak at that location. And we did. This is a counting rate of those particles created at the shock. And you can see we were started in 2003, we began to see them leaking a little bit upstream. And then suddenly, at the end of 2004, boom, there's the shock. Those are the particles which have gotten 1% the speed of light. That was in December of 2004. The distance from the sun, 94 times that from the Earth to the sun, or 8.7 billion miles. So that's where the shock was, up north, where Voyager 1 was. We then followed on with Voyager 2. So the Voyager 1, right there, okay? Then Voyager 2, which is now coming in the southern hemisphere, going down south. It was there. It was at 84 AU. It was not at 94. It was 10 astronomical units, a billion miles closer to the sun in the south and the north. Well, if you look at this kitchen sink image, you'll notice that, in fact, the termination shock of the water is also closer here than there. Now, why is that? I mean, the water pressure inside is equal everywhere. It's because there's a sink wall over here which pushes back on the water over here, and therefore it cannot move as far outward from the source. But there's no sink wall in space. What's out there? What is pushing in on the south? Probably an interstellar magnetic field. And it has to be angled in such a way that it pushes harder on the south. So it has to be tilted like this to push harder on the south than on the north. And this, again, is a mathematical model showing that if you put a magnetic field in and tilt it like this, that, in fact, you can cause a termination shock to occur at 84 AU in the south and at 94 AU in the north. So even though we haven't gotten there yet, we have already learned something about the magnetic field outside. It has to have a certain minimum strength in order to cause that much distortion, and it has to have a certain particular direction to cause the distortion in the south. So what's the next step was as we move out, we expected the winds to turn and flow down like this. We would see as we moved from here on out that the wind would slowly but surely turn from being radial outward to being like this. What we actually saw, and this is now the speed of the wind, this is kilometers per second here. So this is 200,000 miles per hour right here. Instead of seeing it turn, what we saw was it slowing down and basically stopping. And for the last 2 years, the wind where Voyager 1 is hasn't been moving outward at all. It's been moving sort of just randomly, but not outward. And that was not in any of our models. We had expected it would turn, and this wind was not turning, and has not been turning now for over 2 years. So we had entered what we're calling a stagnation region, a region whose thickness we didn't know. We don't know. In fact, we're probably still in it, but that we had entered and we had not expected it. So how do we know when we finally get outside? I mean, we're now in a region where the wind has basically slowed down, but we're still inside. We know we're still inside because we're measuring the magnetic field from the sun inside. So how can we tell? Well, we got a couple of clues that we've been looking for. First of all, one of the clues has to do all those particles that were bouncing around off the shock. You saw them jump up at the shock. They have been steady intensity for the last 7 years. So that's what this cartoon suggests. That is, you have the same density of particles here created at the shock, all being carried out by the wind to this region. Of course, they're not being carried out much here because the wind isn't moving out very much. But once we get into interstellar space, we expect all those particles to disappear. They will escape into the Milky Way. So we would expect one key signature would be to see the number of these particles from the shock slow down, maybe decrease, and then eventually drop, perhaps abruptly, as we crossed into interstellar space. So the things inside will get out, is one simple way of saying it. But there are also particles outside. Those are high energy particles. They're called cosmic rays because the fastest of those can actually get it all the way into Earth. But those with speeds that are too slow, something like 30 or 40% the speed of light only, that's still pretty fast, but it's not fast enough to get in. And so we expect that that they will diffuse in, and that as we approach the boundary of our heliosphere, we'll see more and more of the particles from the outside until suddenly we're outside and we'll, for the first time, see how many are really out there. We just don't know how many are out there. So we expect particles inside to be leaking out and particles outside to be leaking in. And those should be two of the key signatures that we should expect to see. So let me show you what the latest data looks like. This is now the last 3 years of data, starting back in 2009, 2010, 2011, 2012. This is the counting rate of the particles coming in from outside. These are the cosmic rays that were produced by these exploding stars 5 or 10 million years ago and gained enough energy that they can actually diffuse a ways in. And you can see, indeed, over the last 3 years, the counting rate was climbing as we were approaching the boundary with interstellar space. It increased at about 9% a year over the last 3 years. In fact, that's been fairly characteristic for the last 7 or 8 years. And then in May 7th, we saw that. And suddenly, in 1 week, it increased by 5%. And in 1 month by 9%, as much as it had in a year for the last 3 years. So that obviously got our attention. Were we getting really close, or had we in fact possibly entered interstellar space? So that's what's one part of the story, right? The particles outside getting in. The other part of the story is what happened to the particles inside. Did they get out? So here is the counting rate of the particles inside, which had been steady, more or less steady at this rate of about 27 per second for the last 7 years. And here's May, no significant change to those particles. So we clearly had not gotten outside, but something had happened. We had somehow gotten better connected to the outside, but we had not lost any of the particles from the inside. So, but we started obviously looking at our data every day, thinking that maybe something interesting was about to happen. So there's the month of June, and indeed it was slowing down a little bit. I mean, the intensity was dropping a little bit. As I said, we might expect that as we get close, we would start losing some of the intensity out the boundary. In July, oops, just increased a bit again. So, but then it dropped to half in 1 day, 1/2. And 5 days later, right back. This is exploration, right? Nothing had ever been there before. And so every day we look at the data. And there was another one in August. That one lasted 7 days and dropped down to just 1/3 of the intensity it had been. And that was the end of August. It had dropped down to 10%, dropped down to only 10% of the particles remaining that had been inside. And this is what it looks like today. This is only 2 days old now, and you can see it stayed down. So we're now been 20 days where the intensity of the particles that were produced inside has dropped by more than 90%. And we don't know exactly how low it is yet, because we have to work hard now to get the proper calibration, because this is so different than anything we've ever seen before. But I'm confident that we have lost most, if not all, of the particles on the inside. Now what about, now as I said, we started back in May with the first step up with the particles coming from outside. What happened to them during this time? Well, that's this top plot. This is the particles coming in from outside. And you can see this is now just June, so in May they had stepped up a bit in May. And you can see a jump up exactly when that dropped. And it dropped back down when this came back up. And then it jumped up again when that dropped. And it dropped back down when that came up. And then it jumped up and it stayed up when this dropped down and stayed down. It is as though we are now in a region that is well connected to the outside. And the stuff was inside is getting out easily, and the stuff which is outside, the cosmic rays, are getting in easily. Exactly how that happens, we don't know. It's possible, of course, we are actually really outside. And so the question is, are we actually outside the heliosphere? Did we actually leave the heliosphere here, and we're in interstellar space? Or did we just enter a new region of the heliosphere, which is well connected, but we're still inside? Now you might say, how can we tell the difference? We can tell the difference by where the magnetic field is coming from. Inside, the magnetic field comes from the sun. Outside, it comes from the galaxy. And the direction outside should be different than the direction inside. So here are the two possibilities in cartoon form. We found this, we entered this quasi-stagnation region in April of 2010. That's when the winds sort of just came to a halt. And then just this month, just in August, end of August, beginning of September, we entered this region that seems to be connected to the outside, or we actually entered interstellar space. We do not know which picture, if is correct, or if there is some other explanation. That's what we're learning every day as we look at our data. So how can we tell? Here's this is the magnetic field of the sun. We're now looking down on the sun. So you're looking down on, say, the sun's north pole. And as I showed you in the movie, the sun is rotating. If the sun weren't rotating, that radial wind would carry the magnetic field out straight, just as it's drawn here. So this was what the magnetic field of the sun would look like if the sun were not rotating. But the sun rotates. And so what happens is, oops, sorry. What happened here? What happens, I'm sorry, I've got to find my arrow. There it is. What happens as the sun rotates is, of course, the foot of the field line remains anchored on the sun. And so the field line is drawn out into a huge spiral around the sun, expanding further and further out. And so the field is basically the spiral field. And so inside, the field looks east-west. It goes around in a big circle, perpendicular to the rotation axis of the sun. So inside, we have seen ever since the space age that the magnetic field inside is always basically in the plane of it's parallel to the plane of the planets. Outside, it's got to be some different angle. We don't know exactly what it is. We have this model which suggests it might be a rather inclined angle. Rather than like this, it might be more like that. But this is a simple PowerPoint cartoon to show here's the spiral field wrapped around in a big cone around the sun. And that's what we measure when we're inside. And when we go outside, suddenly we should see the field going up and down or something like that. And we're now actively looking at the models very carefully to see exactly what the signature should be, because this may be the key way that we know whether we're inside or outside. We do not yet know. We do not yet have the magnetic field data analyzed to the point where we can say whether this last month we left the heliosphere behind or if we're just in a new region. That's work that is still yet to be done. So I can't tell you. It could have already happened. It may be days, it may be months, it could be several more years. We just don't know. At least today we don't know. Maybe a month from now we will know. Voyager 1 is 11 billion miles from Earth today. Voyager 2 is 9 billion miles from Earth. We have, because of the radioactive power supply, we have enough power to keep all of our instruments running until 2020, and then we'll have to turn them off one at a time as the power continues to decay away until about 2025, when we'll have to shut off the last instrument. So I think that the likelihood of reaching interstellar space before that is very high. It may be already happened. In any case, the journey continues, and I'll be happy to answer any questions. Thank you. If we could have some lights, then we could see if there are any questions. Could we have some lights? There we go. Okay, I hope there's a question or two. Yes, right here in front. Good.
How many watts is the satellite putting out, and is there a problem detecting that faint signal?
Yeah, the question is how much power, radio power coming back, and how hard it is to detect. We have a 23-watt transmitter on the spacecraft, 23 watts. And the data comes back at a very low data rate, 160 bits per second. Pretty slow modem, wouldn't it? But that's what we got from 11 billion miles. So we have a set of antennas at 3 places around the Earth called the Deep Space Network. The largest antenna is 70 meters across, and the smaller ones are 34 meters across, and we have to either use one big one or 2 small ones together to catch the signal, but they work fine. And our main challenge is there are lots of other missions out there that need the same antennas, so we don't get tracked 24 hours a day, but we try to get data for a minimum of 4 hours every day, and typically 6 or 8. We often can get 6 or 8 hours of data every day from these two spacecraft. Another thing, as long as the question about the spacecraft, is that these were the first automated spacecraft. They're flown by 3 onboard computers. Each of those 3 computers has 12,000 bytes of memory. Not gigabytes, bytes. But they're the best thing going out there, right? I mean, 1970s technology. That's what happens when you have a spacecraft 35 years old. Yes?
With current technology, if you built a similar spacecraft and you talk about 88 years, how long would a current Voyager 3 be able to go out into interstellar space?
Well, I think the question, how long, the power supply is an 88-year half-life. So if you want it to last longer, you have to start with more power so you can decay more away, or you can use more modern electronics which use less power, but in fact most of the power goes to the radio transmission, so you probably can't reduce it very much. So the main way you would get a longer life would be to have even to fly, instead of 3 of these generators, fly 5 or 6 or 7 of them. And that you could do, take a bigger launch vehicle, but you could do it. Yeah.
You mentioned that some of the instruments have been turned off. I assume the cameras are no longer valued, but are there any things that you see that are going to be turned off first, and in what order? What do you see as the most important?
Yeah, okay, what's going to be turned off first?
Any of you lost anything? Has anything give up on you that you're hoping would still work?
Well, we have on Voyager 2, we have 5 instruments working, one which measures the wind itself. We can measure its speed and its density and its temperature. One which measures the low-energy ions that are created inside the heliosphere. One which measures the high-energy particles coming from the outside. Another one which measures the magnetic field of the sun. And the 5th one measures the radio waves which are coming from out there. Those are the 5. Of those 5, the one measuring the wind is not working on Voyager 1. So we have just 4 on Voyager 1. And which one would be turned off first will be something that there's no need to determine that today, because we don't have to do this until 2020, and things could break between now and then. But ultimately, in the end, the last instrument turned off will be the one that uses the least power. So probably the magnetometer, because it only uses a few watts, while the energetic particle experiments use 15 watts each. So it's that kind of juggling which will have to be done when the time comes. Yes, there.
I thought I saw some temperatures of 10,000 degrees at the edge of the heliosphere. Did I see that or not?
Yeah, the interstellar wind temperature is about 7,000 degrees.
Are you going to incinerate the Voyager?
Oh, that's a good question. No, I should have pointed out that all of this is going on, but in fact, the density of particles, even at 1 astronomical unit, is 5 particles in a cubic centimeter. 5 atoms in a cubic centimeter. This is a better vacuum than anything here on Earth. So the spacecraft itself is totally oblivious to everything. Only our sensitive instruments know all this is happening. It's almost a perfect vacuum, but not completely empty. So the temperature doesn't matter. I mean, it's just a few atoms hitting us here and there. Doesn't matter. There's one. Got some more questions down here too.
So when you were setting the final trajectory, was that determined entirely on the planetary encounters, or did you know at that time that you were sending it away from the farthest region of the heliosheath and the place where you're most likely to actually penetrate to interstellar space?
Well, you know, in this business, there's a lot of luck involved. The mission was clearly determined by where the planets were. And they totally determined what Voyager 1 was going to do, because it flew by Saturn in such a way that it did that. And that clearly determined what Voyager 2 did, was the planets. But at the same time, we knew that we were lucky, that we just happened, every 176 years when they're all lined up like this, it happened to be on the side of the sun headed toward the shortest way out. Pure luck, pure luck.
Are there more than 2 Voyager missions?
There are 2 Voyager spacecraft, Voyager 1 and Voyager 2. Now, I know Star Trek had Voyager 6. But We have only 2. There's a question down here.
If you were to design another spacecraft to go, what would you choose and what would you put on it? Where would you shoot it?
Well, I think I think it would be important to try to improve the launch vehicle technology so we could go much faster. I mean, it has been 35 years, and it's really a very long mission. So, and you cannot be sure everything will work for 35 years. I mean, luck is involved. After all, space age is only 20 years old. There's no way to have said we knew how to design something that would last 35 years. We didn't. We just did the best we could, and it worked for 35 years. We knew the power supply was good. That's physics. But the engineering parts, you can't depend on. So that's the reason it's hard to think of a mission that really has not done anything new for 30 years. Voyager's had a lot to do along the way because nothing has ever been anywhere Voyager's been before, so it's all been new. But once Voyager's done it, you really need to get out there much faster so you get to the new ground more quickly. And that means improved launch vehicle technology of some sort. Yeah?
Back in '77, what was the approximate cost of these Voyagers, and if we equate that to something built in today's society, what would it cost?
Well, the cost, I can only sort of remember, but it seems to me that the cost through launch was about $250 million, and those are your dollars, so you'd have to take into account the change in the dollars. But a mission like the Hubble is measured in the billions of dollars, so it's all yeah. But this mission has been going now for 40 years. I started on this mission. We launched in 1977. We actually started building it in 1972. So I've been working on this mission for 40 years. And I suspect if you add up all the money that's been spent over that 40 years, it's about $1 billion over 40 years. Yes?
One more question. There are plaques on the side of the spacecraft indicating where they came from. Who would be most likely to see those plaques?
You. No, I'm serious. I think the most important thing about those plaques, actually the plaques are covers on a record, a grooved record, which has on it languages of Earth, music of Earth, sounds of Earth, and pictures of Earth on a double-sided 16 2/3 RPM grooved record. And yeah, I think from my point of view, the most important message was to all of us that we had finally, as a civilization, been able to send such a message. This message will be orbiting the center of our galaxy basically forever, along with all the stars. I mean, it is out, it's gone, it will never come back. Whether it will ever be found, I did a calculation once and I asked myself the question, what's the probability that Voyager will be as close to another star as it is to the sun today in the next billion years? Less than 1%. Less than 1%. Space is empty. And so it doesn't mean it won't be found, but it's not going to be an accident if it's found. I mean, it'll have to be something really super smart because we don't know how to do it. We would not know how to find it today. It's gone. Yes?
Galactic magnetic field. Possible source?
Oh, the galactic magnetic field? Yeah, well, the whole galaxy is rotating. I think that the general feeling is that the magnetic field in the galaxy tends to follow along the spiral arms. It's like threading the spiral arms. But what happens when these supernovae blow up is they distort that magnetic field and capture it and create shells of it. So we're in one of the shells that has been, where the magnetic field of the Milky Way has been captured in the shell. So I think it's this explosion nearby that have really deformed the field in the direction that we expect to find. But we don't know. These are all models. And Voyager will be the first interstellar spacecraft. The only question is, will it still be calling home? I hope it will be. Yes?
How international is your study group?
Well, the Voyager team itself was formed in 1972 at the height of the Cold War, and basically this was basically a U.S. mission. It is still today a U.S. mission. Only the U.S. has the capability of building the RTG power supplies, which are an essential part of the mission. The rover, the Curiosity rover, which is there on Mars now as of the last month or two, has exactly the same kind of power supply on it, which means it will be able to rove for many, many years and doesn't have to go hibernate when it gets cold or when it's the wintertime on Mars. So because of exactly the same robust power supply. And only the U.S. has that capability.
So are there symposia where you glean other ideas from other people in other parts of the world to say, no, I don't agree with your Heliosphere?
Absolutely, absolutely. Once the data is published, we have meetings, and the meetings indeed do involve people from around the world. And there's a very important group modeling the heliosphere in Moscow that we interact with. There's another important group in Huntsville, Georgia that we interact with, for instance. So yes, there are areas of expertise around the world, and of course the Voyager data is really stimulating that, because the way fields progress is when there are observations to help guide the theory, because these are things you can, as I tried to explain, no matter how smart we thought we were, we kept getting surprised. That's where there really is scientific opportunity, when you see things that you haven't already thought you understood, when you see things you didn't even know you were to see. And that's what's still happening to us. Okay. Yes, one more? Last one.
Kind of competition, I guess, but is Pioneer still send back data?
No, the Pioneer 10 and 11 had exactly the same kind of power supply, but they didn't have as much of it. And the last signal from Pioneer 10 was back in the 1990s, and the last one from Pioneer 11, and then from Pioneer 10, it was 2004. So right now, the two Voyager spacecraft are the longest operational spacecraft ever launched at 35. Okay, thank you.
Thank you again, Dr. Stone, for a wonderful presentation that truly was in the spirit of imagining and the spirit of keeping Dave's memory alive. I'd like to thank all of you for attending, and I'm going to already invite you to next year's lecture, which will be September 26th and 27th, the evening of the 26th and the morning of the 27th. If you are able to attend, you'll be treated to an amazing story of human achievement and generosity. Dr. Boachi Aji will be our speaker. He was one of over 40 children of a tribal chieftain, almost died of starvation as a child, arrived here in the United States with only the clothes on his back, and now has had a remarkable career as a spine surgeon and a humanitarian. So look forward to next year as well. This amazing auditorium and this lecture series have been made possible by very generous donors, and we are extremely thankful for that. Any additional support for the lecture series will be deeply appreciated. There will be an encore presentation of this talk tomorrow morning at 7 a.m. here in the auditorium, and you're welcome to come for a repeat if you'd like. And now we'll retire for a reception in the foyer here, and I hope you can stay and join us. Thank you.